All right, last time we talked about constant speed or average speed, but we didn't find a lot of detail. I had an example where a ball was rolling down a plane. We were able to find its average speed, but we didn't know anything about its speed anywhere along the path. Now we're going to start talking about accelerated motion. We're going to be able to do a lot more detail. Problems end up becoming a lot more interesting. So first we're going to define acceleration. Acceleration is a change in velocity over time. Okay, the equation, we could write that in equation form. A is delta V over delta T. So that's going to be important. That equation is not on a reference table, but it's one that's really important. It's the definition of velocity. Now, velocity can be changed in three ways. All right, it should be obvious one thing, and we talk about acceleration all the time. It means to speed up. We say that something's accelerating is speeding up. But there's another way I could change the velocity. I could also slow down. And that's also considered an acceleration. In the English language, we say deceleration. But in physics, we say it has an acceleration that's causing it to slow down. And the third one is not one we think of, but if we change direction, that's also going to be a change in velocity. Because velocity is a vector, so a change in direction is going to change the velocity. So any one of those will cause an acceleration. Now, in this unit, we're going to be dealing with speeding up and slowing down. We're not going to be dealing with a change in direction, but when we study circular motion, we will be talking about that. So in which of the following examples is the object not accelerating? If I drop it from rest, we know as it falls, it speeds up. So that can't be it. That's definitely accelerating. A car traveling at a constant speed in the same direction. So constant speed, I'm not speeding up, I'm not slowing down, okay? And I'm going the same direction, so I'm not changing direction. So this is definitely going to be not accelerating. All right, constant speed around a circular track. If I'm going around a circular track, I'm changing direction. Okay, so maybe make a note of that. This is a change in direction. So that is accelerating. Okay, and then the last one is a ball rolling to stop along a level floor. Again, it's slowing down. Okay, so that is going to be an acceleration. So the only one where it's not accelerating is going at a constant speed in the same direction. Now here's the equations we're going to use, and the trick is going to be deciding which equation to use for any given problem. I'm going to talk about that a little bit in a minute. We have to know what each of the variables means as well. A right here, okay, stands for acceleration. V0 is initial speed, the speed you start at. V is the instantaneous speed, the speed at any point that you're interested in. It could be at the end of the problem, or it could be after 1 second, but some time or some speed somewhere along the path of the object. T is time, and delta x is displacement. The acceleration of gravity is a special one. If we talk about dropping a ball, we know the acceleration is going to be 9.8 meters per second. Now we can approximate that with 10. Okay, so we'll write approximately. All right, so it's approximately 10, and we're going to use 10 most of the time when we do these problems to make our math easier. Now, how to solve these problems, or any problem, okay, is the following. You're going to identify your givens. All right, that's going to be the first step. The second step, and this is actually very important, is identify what you're looking for. Okay, and so I'm going to put a big explanation points by that, because that's going to be the most important thing. On the AP exam and even the Regents exam, they have a lot of words, right? They write a big long paragraph, and in there you get lost. And you have to ask yourself, what am I looking for? And underline that. Pay really close attention to that. And then the last step is going to be to find the appropriate equation. Okay, when people are having problems, a lot of times it's because they're picking an equation and trying to stuff their rails into it. So they think, oh, I know it's going to be this equation right here, and then they try to plug the variables into it when it's not supposed to be that equation at all. So that's the last step in problem solving, is find the equation and solve it. A lot of times I find that I spend most of my time when I'm walking around the room helping people saying, what are your givens? What are you looking for? What equation are you going to use? I don't actually help with a problem at all. I just step through these steps. So if you get in your head, these are the steps you're going to use to find them, to solve the problems, you're going to be able to solve the problems on your own. So here's our first example. A car is traveling at 20 meters per second. Now what is that 20 meters per second? That's information I'm going to use, okay? Well, that's speed, and it's at the beginning of the problem. So that's going to be V0. So I'm going to write down V0 is 20 meters per second. Then it puts on its brakes and comes to a stop while covering a distance of 80 meters. Distance of 80 meters, for distance or displacement, we've been using the equation delta x. Delta x is 80 meters. Now, there's actually a third variable that's given in here. It's given kind of subtly, okay? It says it comes to a stop, okay? When it's stopped, I know its velocity is 0. So its instantaneous velocity at the end of the problem is going to be 0. And then, the other thing is, what am I looking for? What is the car's acceleration is the last sentence. So A is what I'm looking for. Now I have to find the appropriate equation. So I want an equation with V0, delta x, V, and A. And here's a hint. It can't have T in it because T isn't one of my givens. It's not what I'm looking for. So now as I look back up my equations, it can't be this one, okay, because that has T in it. Okay, can't be the next one. Oh, here it is. Okay, this has V0, V, A, and delta x without T. So that's the equation I'm going to use. So V squared is V0 squared plus 2A delta x. 0 was V, so 0 equals V0 squared, so 20 squared plus 2. I'm looking for the acceleration, so I'll leave that as A, and delta x is 20. Oops, I'm sorry. Delta x is 80. Now, as I do this, this is 0. 20 squared is 400, plus 160, because 2 times 80 is 160 times A. Then my next step, I would subtract 400 from both sides. You'll notice that I don't show all of the detail, and you don't have to. In math class, I like to show minus 400 on one side, minus 400 on the other side. It's neater and quicker to do it this way. If you want to show all the steps, you can, though. And then my last step, I would divide by 160, and I would get A equals negative 2.5 meters per second squared. Now, what does that negative mean? It turns out this thing is slowing down. We gave it a positive velocity to begin with. In order to slow down, the acceleration has to push in the opposite direction. That's what the negative stands for. So a lot of times when things are slowing down, you're going to have a negative acceleration. Our next example is at the top of the next page. This is about as tricky as I can make these. A ball is thrown upward with an initial speed of 30. How long will it be in the air? It seems like we only have one unknown, or one given. We have V0 equals 30 meters per second. One thing that helps a lot of times is drawing a sketch, so I'm going to do that. So if I think about this ball, it's here. It starts out going upward with an initial velocity of 30, goes up to its high point, and falls back down. Now, there's two things I know about this. One is the acceleration is negative 10 meters per second squared. It's just gravity. All right, remember gravity is 9.8. We're going to approximate it with 10. Now, the reason I make it negative, V0 was positive going upward. Gravity always pulls down in the opposite direction. So if up is positive, down is going to have to be negative. I also know that on the way up it's going to slow down, and negative accelerations tend to make things slow down. Now, we need one more variable. For all of these equations, we need 3 things known. And here's the trick to this one. What I do is I look at this point, okay, and at the very top, I know something about it. On its way up, the velocity is positive. On its way down, the velocity is going to be negative, because down we're going to call it negative. So at the very top, it's not negative or positive. Its velocity is 0. Momentarily, instantaneously at the top, its velocity is 0. So now I know v equals 0 at the top. And that's why this is a trick question, because you had two kind of hidden variables. The acceleration was gravity, and the velocity at the top was 0. But now I have three things I can find what I'm looking for. That very important step is identify your unknown. It says how long. How long is time? I'm looking for time. Now I have to go back and find an equation. So let's do that. We'll look back at our equations. All right, this one had v, v0, a, and t in it, and it turns out it's going to be this equation right here. It might be a good idea to have a page in your notebook where you just write down all the equations we've been using, and then you can always refer to that rather than flipping through the notes trying to find the equations. So v equals v0 plus at. V is 0 equals 30 for v0 plus minus 10 for a times t. Subtract 30 from both sides. I get minus 30 equals minus 10t. And if I divide by 10, I get t equals 3 seconds. That's not actually the answer. See if you can think of why that is not the answer to the question. And the reason why is this. This is the time to the top. But that's not what it was asking for. It was asking for how long would it be in the air. And it turns out that this is symmetrical. It's going to take as long to go up as it does to go down. So the total time is going to be 6 seconds. So that's the answer to that question.